Hello Chem 1B, this is chapter 17, lecture video 7, and we're going to finally get away from acid-base equilibrium. So we've talked a lot about equilibrium over the last 3 chapters, including this one. When we first talked about it, we just talked about regular KQ or KP, KC type situations. Then in chapter 16, we started talking about acid-base reactions, so KAs and KBs. And we know in a Ka equilibrium, we're forming our H3O plus in solution, and in Kb, we're forming OH minus. We also talked about Kw, the autoionization of water. Well, we actually have 2 more equilibrium constants that are special to talk about, and the next one is known as the solubility product constant, or in other words, KSP. Still just a regular equilibrium constant, but it's for solubility equilibriums, which are kind of special. As you might notice here, on our reactant side of this reaction, we have a solid, and that's it. And that is true of pretty much all solubility equilibriums. We start with the solid and we dissolve it into its ions. Now, what this means is, if you remember, solids we do not include in the equilibrium expressions, so KSP is always just something times something. With no denominator. So let's get a little bit more into this. So let's look at this equilibrium, right? Like I was saying on the previous slide, if we look at the equilibrium expression, we think products over reactants, but it's really important to note, right, that the solid does not get included. And this is true of all KSPs. We generally just have a numerator. We do not have a denominator for our equilibrium expression for KSP values, or solubility product constants. So KSP is what we call the solubility product constant, and you can find it in your textbook in the index, just like our Ka, Kb, and Keq values. It's for saturated solutions. So if you remember from Chem 1A, a saturated solution is where we've hit the equilibrium limit for dissolving our salt in water, mostly. Generally, this means that we have to have some solid present in the system because you have to be at equilibrium if you're there, and then that means you have both products and reactants present. So there's generally a little bit of solid present when you have a saturated solution. One of the things to really make sure you guys understand is that solubility and KSP are not they're not the same thing. KSPs will allow you to calculate the solubility, and if you know the solubility, you can calculate the KSP, but they're 2 different quantities. KSP is an equilibrium constant. Solubility depends on the conditions of the solutions. So KSP is a constant, just like all equilibriums. It's constants, its value is fixed, with the exception of temperature, right? If we change temperature, KSP will change as well. Solubility is really the amount that is dissolved into the solution, and that can vary depending on what conditions are present in the solution. Is it acidic? Is it basic? Is it, is there something else going on that's causing the solubility to increase or decrease? There's a lot of variability here. Now, solubility has units of milligrams per liter. This is more of an engineering type unit. Generally, chemists use what we call molar solubility. Unless I tell you otherwise, when I ask you to solve for solubility, I'm always asking for the molar solubility of the solid in that solution. Moles per liter obviously is molarity, right? So that's generally what we calculate solubility in terms of, as in a chemistry course at least. All right, so just like before, Q is making a comeback, right? Q was in chapter 15. If you remember, it allows us to determine which direction in equilibrium is going to shift based on the initial concentrations of stuff present in the solution. So if we look at this equilibrium, right, Q is still just going to be the equilibrium constant expression under initial or unknown conditions. As to whether or not we're at equilibrium or not, don't know. Cool, we're calculating Q. And really, a lot of this is the same as what we learned about before, right? If Q is greater than K, we learned that the shift will go towards the reactant side. Well, that's still true. If Q is greater than KSP, we're going to shift towards the reactants. Well, our reactants are in the solid state, so that means we're going to form an insoluble solid. A precipitation reaction is going to occur until we reach equilibrium again, where Q is equal to KSP. If Q is equal to KSP, we have a saturated solution and we're at equilibrium. Now this is where it gets a little different. If Q is less than KSP, we don't suddenly have a shift this way. That's technically not really what's occurring. What's occurring is we don't have anything happen really. The solid will dissolve until we reach Q is equal to KSP. So if I add barium sulfate and it completely dissolves, it'll all go to this side. So we do have a shift to the products, but the reaction will stop. We won't reach equilibrium because there's not enough of this to go backwards yet. So if Q is less than K, we just form products and that's it. There is no reactants left. We do not reach equilibrium, which is kind of different from what we've seen in the past. Now, we're going to talk about this in a later lecture video, but using solubilities, we can actually selectively remove stuff from solutions. Maybe I want to get rid of all of the silver ion present in my solution. Well, I can do that using solubility. Now, this is basically what a lot of the qualitative analysis that we're doing in Canvas labs throughout the course are about. So let's talk about pH and its effect on solubility. So if we have an acidic or basic salt, pH will affect its solubility. So this is basically going to just be a summary of how to determine whether a salt is weak, acidic or basic or neutral, which was something we covered in chapter 16. If the anion of a salt is the conjugate base of a weak acid or it is a hydroxide, then it is a base, right? It's a basic salt. And if we have a basic salt, the pH is going to affect the solubility of that salt. If the anion is the conjugate of a strong acid, then it's a neutral salt and is therefore not affected by pH, right? Now there's a cation part of this too that we should know about as well from chapter 16. At the end of the day, basically, if your salt is an acidic salt, pH will affect its solubility. If your salt is a basic salt, pH is going to affect its solubility. If your salt is a neutral salt, pH will not affect the solubility of that salt. So, if we look at AgCl, we need to determine, is this salt a neutral salt, acidic salt, or a basic salt? And that will tell us whether or not the solubility of this salt will be affected by pH. Now, if you remember, we got to look at the cations first and ask ourselves, is this a neutral or acidic cation? And the answer to that question is Ag plus is neutral. It's one of the neutral cations we learned about in chapter 16. And Cl minus is the conjugate of a strong acid, which means it's also neutral. So this salt, AgCl, is a neutral salt, which means that pH will not affect its solubility. If we look at BaF2, barium, we got to break it apart again, right? Barium is Ba2 plus, and it's an alkaline earth metal, which, if we remember from chapter 16, is a neutral cation. This guy here is F minus, which is a weak base. That makes this salt a basic salt, right? So its solubility is definitely going to be affected by pH. If we look at aluminum hydroxide, absolutely this thing is going to be affected by pH because we have hydroxide. That's a dead giveaway. Anytime you see OH minus, the solubility of that salt will definitely be affected by the pH of the solution. All right. So it's not an eye-clicker problem, but it's still a relevant question, right? Which of the following ionic compounds will pH affect the solubility? So again, we're just basically doing exactly what we did on the previous slide. breaking these down and determining which one is our acidic, basic salts. Those ones will have their pH affected by solubility, or sorry, their solubility affected by pH. And the neutral salts, they won't. So we look at NaCl, Na, that's neutral. And Cl minus, that's neutral. They're both neutral. This is a neutral salt. pH is not going to affect the solubility. Li plus, also neutral. ClO4 minus, conjugate of a strong acid, also neutral. pH will not affect the solubility. This guy is Cr3 plus, and we also have NO3 minus. Now NO3 minus is the conjugate of a strong acid, so it's neutral. But Cr3 plus is acidic because it's not one of the cations that we know is neutral. So this is our actual answer here. Its solubility is definitely going to be dependent on pH. Now calcium bromide, if we look at that, Ca2 plus is also neutral. It's an alkaline earth metal, and Br minus is the conjugate of a strong acid, so it's also neutral. So the only one that is at all acidic or basic is this guy, and therefore its solubility definitely will be affected by pH. So if you have any questions, let me know. My discussion sessions or email are the best ways to get a hold of me.